Hello, everyone. Today, I'll be talking about SciKit-Learn with Dask and Intel extension. We would look at the current state of GPU utilization in SciKit-Learn. Then I will take you through the process of enabling GPU support in SciKit-Learn using Intel extension for SciKit-Learn. I would do a demo of this on Intel Developer Cloud to show you how you can leverage Intel CPUs and GPUs to accelerate computations on SciKit-Learn. I will also take you through the process of setting up RAPIDS on Nvidia machine. So I'll be doing a demo of this on a ALCF Polaris to show you how we can set up RAPIDS to leverage GPUs for machine learning tasks. I know most of us are very familiar with SciKit-Learn. SciKit-Learn is a very popular machine learning algorithm in Python that is known for its efficiency in handling a wide range of machine learning tasks. SciKit-Learn was designed to provide simple and efficient tools for data mining and data analysis. It was built on top of NumPy for numerical computations, SciPy for handling a wide range of scientific and engineering tasks, and the Matplotlib for visualizations. SciKit-Learn is very easy to use, and in terms of performance, it's relatively okay. But even though its performance is okay, there is still room for improvement to achieve better performance. One interesting thing about SciKit-Learn is its ability to interoperate with other machine learning libraries. However, one common question within the machine learning community, this question is common within this community, as most data scientists and machine learning practitioners will always ask if it is possible to leverage GPUs to accelerate computations for SciKit-Learn. Well, natively, SciKit-Learn does not support running on GPUs due to several reasons, one of which I would refer to as algorithmic constraints. Many of the algorithms in SciKit-Learn were designed in Python, and these algorithms were optimized for CPU-based computations. So adapting these algorithms to leverage GPUs would require significant changes. And even after making these changes, you may still not get the required performance improvement. Also, introducing GPU support to SciKit-Learn would require additional software dependencies and hardware-specific configurations. This would complicate the installation and maintenance processes for users and developers. Another reason is what we would refer to as design constraints. SciKit-Learn focuses mainly on providing a unified API for basic machine learning tasks. So adding GPU support would require a redesign of the SciKit-Learn package, and this would complicate and make the maintenance process very complex. However, despite all these challenges, there has been some significant efforts towards enabling partial GPU support in SciKit-Learn. This has been done through the Array API. In 2023, yes, SciKit-Learn introduced partial GPU support via the Array API. So with this, certain SciKit-Learn estimators can run on GPUs, but that is only if the input data is provided as a PyTorch or CuPy array. But this support is still limited because only certain estimators can be supported at this time. Also, Intel has developed an extension for SciKit-Learn. With this extension, some SciKit-Learn estimators can now leverage Intel CPUs and GPUs to accelerate computations. What the Intel extension does is that it patches the scikit-learn estimators. That is, it replaces the traditional scikit-learn estimators with versions of that estimator that uses vectorized instructions like the Intel's advanced vector extension. So with this, we can get a performance boost without changing the existing API. So with Intel extension for scikit-learn, you can get significant performance boost, just like I said, without relying on a different library. So you don't have to change your code. And one good thing about the Intel extension for scikit-learn is that it supports the Intel's One API concept. This means that your code can easily run on different devices like CPUs, GPUs, without having to do any significant code modification. And it is very easy to enable Intel extension for scikit-learn. You can do this either through the command line interface by just calling the sklearnx. So with just this single line of code, you can enable Intel extension for scikit-learn while running your application. So with this, you can optimize all versions of scikit-learn estimators that are present within your script. Again, you can enable Intel extension for scikit-learn from within your script using just these 2 lines of code. So you can import patch sklearn from sklearnx and then call the patch sklearn method. So with this, you are replacing the traditional scikit-learn algorithm with versions of those algorithms that uses vectorized instructions. So you get an optimized version of these algorithms by calling the patch sklearn. Like I said previously, the support is still very limited because not all scikit-learn estimators can support Intel extension at this time. I have listed some of the algorithms that are supported at this time here. So clustering algorithms like DB-scan, density-based spatial clustering of application with noise is currently supported. K-means also currently supported. For classification algorithms, random forest classifier is supported, logistic regression is supported, and the k-nearest neighbor, as well as a support vector classifier, are all a classification algorithm that are supported by Intel extensions. For regression, random forest regressor is supported. Linear regression is also supported. K-nearest neighbor is supported. And for dimensionality reduction, principal component analysis is also supported. So these algorithms I have listed here can leverage GPUs, Intel GPUs, to accelerate computations. For CPUs, there are several algorithms, several scikit-learn estimators that can leverage Intel CPUs for accelerating computations with Intel extensions. So I have provided the link to these algorithms here. So you can just check through the link to see a list of these algorithms. So without wasting much time, I would go straight to the hands-on demo of this. So like I mentioned previously, we will do a demo of this on Intel Developer Cloud. So I have a coupon here, which you can use to get some time to run this demo on Intel Developer Cloud. So all you need to do is to log into Intel Developer Cloud Console. So we will just log in. Yeah. Yes. Okay, I think this is it. We're here. So to log in, we need to, first of all, register. So you need to create an account. But I already have an account, so I will just sign in. So once you have your account created, you can sign in using the email address with which you have created the account. And then you can provide your password and then may send you a verification code to either your email or the phone number you supplied during registration. So I have the code already. I'll just supply code and verify. So once verified, you'll be taken to the Intel Developer Cloud Console. And when you are there, you can just get into learning, click on Connect Now, and then click on GPU. Then you can now launch notebook. We are going to be running this demo on a notebook. So this notebook is also available here. This notebook is available on GitHub on the ALCF Hands-on HPC Workshop repo. So you can just do a git clone to clone this file, and then you can find the scikit-learn Intel ext is a notebook, and that is the notebook that contains the script I'm going to be using for this demo. So here's the notebook. So I'll be training a DB-scan model here using the spoken Arabic digit dataset. My interest here is to see the performance in terms of the speed up achieved with Intel extension for scikit-learn versus using the traditional scikit-learn algorithm. So using the spoken Arabic digit dataset for training my DB-scan model. This dataset is freely available on the UCI data repository. First thing first, I would have to import all the libraries I need at this time. So for training my model, as soon as I may need train test split to split my data set into training and testing set. I would also need a metric to evaluate the performance of my clustering algorithm. And then I'll be using a fetch open ML to fetch this data. So I'll download the data and then normalize my data to make sure that all the features are having equal contribution to making a predictions. So like I said, our interest here is to see the speed up achieved with Intel extension for SciKit-Learn. So to enable Intel extension for SciKit-Learn, I would import patch sklearn from sklearnx. But before, in case you don't have sklearnx, you may have to first install it. So you can, first of all, make sure that you have a sklearn installed. If you don't have it installed, you might have to do a pip install scikit-learn. You install it, then you can then install scikit-learn IntelliX. So after this installation, that is when you can now be able to import, you can now be able to import patch sklearn from sklearnx. So once imported, you can now call a patch sklearn method. And if you do that, you can see the message I have here, Intel extension for scikit-learn enabled. So like I said, patching sklearn simply means replacing traditional sklearn algorithms with optimized version of those algorithms. So once patched, I can then train my DB scan clustering. So I'm doing this training on Intel CPU. So once I have patched sklearn, I will have to import dbscan. So the dbscan I'm importing at this time is an optimized version of dbscan from scikit-learn. Then I'm also tracking the time it takes to train the clustering algorithm. Now, it took just 19.60 seconds to train this algorithm with Intel extension for scikit-learn. I would go ahead to evaluate the clustering quality using Davis Baldwin index. So the David Baldwin index score is a metric that measures the quality of clustering by evaluating how well clusters are separated or how well these clusters are compacted. So I have the score already. Why I am doing this is that I would want to train this same model using unpatched scikit-learn. So using the traditional scikit-learn algorithm. And then I want to see how long it took without Intel extension. I want to see how long it will take to train my clustering algorithm. And then I want to be able to see the clustering quality. I want to be able to compare the clustering quality achieved when using Intel extension for scikit-learn with the quality of the clustering when I'm running just my stock scikit-learn algorithm. So to train the same algorithm with original scikit-learn, I need to cancel optimizations. And how do I cancel this? I need to unpatch sklearn. So I will just go ahead and unpatch. So unpatching sklearn means I am returning sklearn from the optimized version. I had it when I patched it. I'm returning it to the original scikit-learn, the unoptimized version. So once unpatched, I will have to import dbscan again. So this time I'm importing dbscan, not the optimized version again, but the original. I'm importing the traditional dbscan from original scikit-learn. So I will train the same, I will fit this I'll fit this model again to my data set, train the same model, just like the way I have done with Intel extension for scikit-learn. And then I'm going to observe how long it takes to perform this training. It's going to take a little bit more time because it's not optimized anymore. So, but while that is going on, I think we should proceed. So, I will also evaluate the quality of this clustering to be able to compare with the Intel extension for scikit-learn version. So, like I said previously, this training was done on a Intel CPU. We can as well leverage GPUs for optimization. So I can train my model on Intel GPU. But for me to be able to do that, we need to have a DPC++ compiler runtime and drivers installed. So you may want to install a DPC++ compiler runtime from either from PyPy or through Anaconda. So you can just use any of these, maybe this to do that installation. So once you have it installed, mhm. Okay, yeah, I think that training is done. Okay, so if you look at it here, it took about 377.92 seconds to train this same model using the same training data set on without the Intel extension for scikit-learn. Whereas with Intel extension for scikit-learn, it only took 19.60 seconds. So you can see the significant improvement here with and without Intel extension. And then if we look at the quality of clustering too, we see the same quality, 0.8543 Davis Bowden score obtained here, same score we obtained when we trained with Intel extension, and the same score we had without Intel extension. But the speed up is very, very high. So let's move to training on GPUs. So, like I mentioned previously, to be able to leverage GPUs, we need to have a DPC++ compiler installed. So you can just either do this using a pip install, or you can install it from Anaconda using a Conda install to do it. So you can use this line of code or this to get it installed. And once installed, we can then import patch sklearn again. So import patch sklearn from sklearnx. We are also going to be importing a config context. So with the config context, we will be able to set the device upon which we want the training to be done. So I'll just call a patch sklearn, and then it tells me that I have it enabled. I have a Intel extension for SciKit-Learn enabled. And then once that is done, I can then train my model again, but this time I'm training on GPU, the first GPU available. So I'm using config context to set my target offload. And with that, I'm selecting, or I'm setting the device where I want the training to be done. I'm also tracking the time it takes to train this model. And as you can see, with training on GPU, it only takes 1.91 seconds. What took me 377.92 seconds to train on original sklearn algorithm, it took me 19.60 seconds to train with Intel extension for SciKit-Learn on CPU. And then on GPU, the same algorithm, the same data set took me about 1.91 seconds to train. So you can see for yourself the benefits of Intel extensions for both optimizing computation on a CPU and the GPUs as well. So if you want to read more on this, or you want to try out some other example with other estimators, then you can check out this link I have here. Yeah. So with this, we can go straight to demonstrate how we can set up rapids on a ALCF Polaris. So we will go straight to setting up rapids on Nvidia architecture. So we'll set up rapids for on Polaris. So Rapids is an open source data analytics and machine learning acceleration platform that leverages GPUs to accelerate computations. Rapid is based on Python, and it has a pandas-like and a scikit-learn-like interfaces. Some of Rapid's API, like a QDF and a QML. QDF is a Python GPU data frame library used for loading data, for joining data, filtering, and performing other forms of data manipulation. So QDF lets you create and manipulate your data frame on GPUs. And the QML is a suite of libraries that implement machine learning algorithms and mathematical functions. And it shares compatible APIs with other Rapids projects. So we can scale Rapids by integrating it with Dask. So if we have a Dask QDF, we can scale from single to multiple GPUs. So we can have our data distributed on multiple GPUs for our training. So I wouldn't take much time explaining this, but I would go straight to setting up rapids on Polaris. So first, you need to get access to Polaris. And to gain access to Polaris, you should just use this SSH, your username. ALCF. So once you do that, you'll be required to enter your password. And that should be your Mobile Pass Plus key. So I'll put in my password. And then with that, you are able to gain access to Polaris. So once you are able to log into Polaris, the very first thing to do might be to clone this Git repo, because that is where we have the script I'll be using to do this demo. So we can do a Git clone. So yes, I'm now cloning the repo. Okay, yeah. So I think that's done. So once you have cloned it, you should see ALCF Hands-on HPC Workshop here. And if you are able to look inside this, let's see. So there are a whole lot of other folders in there, but I'm more interested in the SciKit-Learn folder here. So let's see the content of that folder. Okay, so yes, we have some scripts in here. There are 3 of these scripts which I would like you to move to your home directory. So make sure you move this script, start rapid cluster polaris.sh and the start rapid cluster rank.sh, as well as activate rapid env.sh. So just make sure you move them to your home directory. I already have these scripts here within my home directory, so I want you to move. This is the script we will be using to start up a rapid cluster. Also, within the folder you cloned, there is SciKit-Learn with Dask.ipynb. This is a notebook. This notebook contains more instructions on how we can set up rapids on Polaris. So you can refer to that notebook. Yeah, so this is the notebook. So I have given a step-by-step instruction on how to set up rapids on Polaris. The very first thing to do will be to log into Polaris, just like I have shown you, clone that Git repo, get into this folder, the SciKit-Learn folder, and then move the 3 files I have mentioned previously, start rapids cluster dot sh and the start rapids cluster rank.sh, as well as activate rapids env polaris.sh. Move them to your home directory and make sure you have read and write access to those files. But once you are done with that, the next thing to do will be to submit an interactive job so that you can get a node to run this script on. So what we'll do will be to use QSub to submit an interactive job. So I've just submitted an interactive job. Yes, and I think I have a node already given to me. So we have this node already. Now, once you have your node, from within that node, you should run the script. You should run the script, start rapids clusters polaris.sh. So from this node, I will run this script. So what this script does is that it starts up the clusters. It starts up the clusters. And it will start up the scheduler on the node with one worker per GPU. So once you have been able to start up the rapid cluster, you'll see few messages like this. Once you have done that, one other thing I would like you to do, from that file you cloned, I think you have it, we have it here. From this, I need you to move this script. Open Jupyter Lab Polaris.sh, move this script to your local machine. So this is my local machine. You just move it here. So I have it. Yeah, this one. Open Jupyter Lab Polaris.sh. So move that file to your local machine. Once you have moved it to your local machine, the next thing we will do here would be to access the already running cluster. Remember, this cluster is already running. We've already started up a rapid cluster and it's already running on this node. So the next step will be to establish a multiplex SSH connection to Polaris so that, and to do that, all you have to do will be to run this command from your local machine. What we are trying to do here is to establish a multiplex SSH connection to Polaris so that we are able to access the rapid clusters from Jupyter Lab. So on your local machine, this way you run this SSH tunneling. Make sure you change your username. Change this to your username. And once you have done that, on a separate window, still on your local machine, I want you to start up the script. Open Jupyter Lab Polaris.sh. So yeah, so this one. Okay. Oh yeah. So we need to supply the node. We need to supply the node where, yeah, we need to supply this node where the cluster is running. Okay. Yeah. So supply the node name, and then run that script. So this should return a URL, which we would copy and paste on our browser to be able to access the Jupyter Lab on Polaris from our local machine through the SSH connection we have established. Okay, so we see the URL. All you just have to do, copy this URL and paste it on your browser. And then you can access the folder from within the Jupyter Lab menu. To do that, you may want to create a symbolic link to the cloned file. So I have detailed the steps through which you can create a symbolic link so that you're able to access the cloned file from within your Jupyter Lab. So from your terminal, you may just run this command. And then as soon as you are able to launch Jupyter, you should be able to connect to this folder. And from within this folder, there is a notebook, like I mentioned to you previously, notebook which is named SciKit-Learn with Dask. It's a notebook. That is the notebook that contains this script. So once you are on Jupyter Lab and you are on a Jupyter notebook this way, you want to connect to the cluster from within Jupyter. So all you need to do would be to run this, to add this code, to run this code. So first we imported client, imported a Dask distributed and some other necessary libraries here. And then we are able to connect to the scheduler here. And when I run this cell, I'm able to connect to my scheduler. So here also, just like we did with the Intel GPUs, training DB scan model, and looking at the performance improvement with Intel extension for scikit-learn and the traditional sklearn. Here we are going to do same. We are going to train DBScan model. We are going to see the time it takes to train using RAPIDS. So the very first thing to do will be to also import the libraries I need for this. I'm importing make blobs. I'm importing make blobs because I want to generate some synthetic data for this. I'm importing a SciKit-Learn. I'm also SciKit-Learn. This is SciKit-Learn, the traditional SciKit-Learn. I'm also importing a QDF. Like I mentioned before, QDF is a Python GPU data frame library. So it enables us to load our data on GPUs. And then I'm importing DBScan again. This time I'm importing and I'm importing DBScan from QML. This DBScan is able to run on GPUs. So this version of the DBScan will be able to run on GPUs. Also important time so that I can take I can measure the time it takes to train my model. So the next thing to do will be to generate my synthetic data set. Oh, sorry, I need to run this first. So generate my synthetic data set. Okay. Okay. And once I'm able, okay, so I've been able to generate multiple data set, about 280,000 samples within 2 clusters. I'm going to train my DBScan on GPU. So the very first thing to do will be to convert my pandas data frame into a QDF data frame so as to be able to distribute this data on GPU so that I can run this, I can be able to load my data on GPU. So once I have been able to do that, I can then go ahead and train my DB scan. Look, I'm training this DB scan using the DB scan imported from QMail because this version of DB scan would be able to be trained on GPUs. So, and while training, I'm also looking at the time it takes to complete this training. Okay, so it took about 12.0827 seconds to complete this training on GPU. And again, I'm going to train on CPU to see how long that would take compared to training on GPU. It may take a little longer here because I'm doing this training now on CPU. And once I'm done with this training, I'm also going to compare the result obtained when I trained on GPU versus when I trained on CPUs. But this may take a little time. Okay, so I think the training is done. It took 85.2842 seconds to train on CPUs. So you can see the improvement from training on GPU and CPU. So we had a 12.0827 seconds when trained on GPU and 85.2842 seconds when trained on CPU. So you can see for yourself the benefits of training on GPU. And then when we look at the result obtained, so we looked at the silhouette score as a means to evaluate the quality of the clustering. And when we look at the training done on GPU versus that done on CPU, the quality of clustering are very similar. So after this training, I think the very last thing to do will be to shut down the cluster, so you can run the client.shutdown command. Then you can run the close Jupyter Polaris.sh script on your local machine. Also, this script can also be found on the repo you cloned. So you can run the script to close the session. And with that, we come to the end of the hands-on training for SciKit-Learn with Dask and Intel extension.